Welcome back to the last session of this workshop. The next speaker is Ezequiel Mikulan from the University of Milan here in Italy, and he's going to talk about measuring the brain complexity as an index of the level of consciousness. So please, Ezequiel, the stage is yours.
Okay, so welcome everybody. In this presentation, I will show you how we can measure brain complexity to obtain a reliable index of the level of consciousness that can be used in a clinical setting, that is, with patients suffering from disorders of consciousness. So I will first describe the problem. Okay, so I'll first describe the problem of the input and output on the diagnosis of this type of patients. I will show you some typical approaches to this issue. I'll then show you how to measure brain complexity and how this can be formalized on an objective index called the perturbational complexity index. And then I'll talk about some mechanisms, some putative mechanisms that underlie the loss of complexity that leads to unconsciousness, and I'll show you some work in progress that we have on the topic right now. So, typically in neurology, disorders of consciousness are diagnosed using an input and output paradigm, we could say. If we consider the brain of the subject as a black box, neurologists typically give some commands like follow this light, please move a finger, and so on, and then observe the output. So if the patient moves the finger, follows the light, to assess if they are connected with the environment. But then something happens with many of these patients, that is that they are disconnected. I mean, the output pathways, the motor outputs are blocked, so they cannot produce a behavioral response. This includes locked-in syndromes, where the lesion, typically in the pons, a subcortical structure, blocks motor outputs, and in mesial frontal cortex lesions, where executive functions are disabled, so the patient cannot create the complex pattern of movement or has the volition to reply. So in 2006, Adrian Owen showed a very important finding. So he asked subjects while being on an fMRI scanner to imagine that they were playing tennis or that they were moving around in their apartment, and he showed that these two different tasks produce two very different patterns of activations. So then he took a patient and repeated the experiment and showed that the patient, even though he was completely unable to produce a motor output, his brain was responding to the commands that were given to him. So this same paradigm was then extended as a way to communicate with these patients that would be otherwise disconnected. So in some subjects, this might work. This was done by Martin Monti. In some subjects, this might work, but the sensitivity here was very, very low. So this means that 30 patients that were diagnosed as minimally conscious, therefore with some remaining consciousness, failed to complete the task, probably due to the complexity of performing such a task for a patient. In a similar vein, an ERP evoked potential, the P3B, has been proposed as an index that does not require an output to assess the state of the patient. In this case, a series of tones are presented, for example, beep, 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 boop, beep, 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 boop, beep, 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 boop, and then a final sequence in which the last element is equal to the previous ones. So here there is a local similarity. All of these are similar, but this pattern is different from the patterns that the patient was hearing before, creating a global deviance. And this particular case creates a potential that normally peaks around 300 milliseconds, as is shown as this positivity on the vertex. However, earlier this year, Claire Sergent showed that if you don't ask the subject to actively engage in this task, this potential disappears. And therefore, this becomes very complicated to use in a clinical settings where patients might not be willing to pay attention or paying attention, and so on. So with this type of approaches, the problems are mostly the low sensitivity, I mean, the high number of false negatives that you have, and the complete dependence on input. So these patients have to hear the instructions and require some cognitive functions. So how can we assess the state of the brain in the case of absence of input. I mean, if the subject might be conscious but might not be able to process incoming stimuli. So how do we measure it? In other words, how do we create a brain-based index that is reliable and independent of sensory processing, executive and motor functions? Some approaches to address this issue have been, for example, to measure the level of activity, under the idea that consciousness requires a higher level of activity. But if you look at the spiking activity of neurons during slow wave sleep and an awake state, we can see that even though there are some differences, the difference is not massive. Again, if we look at a PET scan, I mean a scan of the metabolic activity of the brain, we can see that between a conscious and a vegetative state patient, there is a big difference. But when this patient recovers, the recovery does not match the consumption, the metabolism of before, and it's not very, very different from the vegetative state, therefore making it a bit unreliable, even though this patient was perfectly conscious. Another measure is synchrony. So it's been shown many, many times that conscious processing of sensory stimuli requires some degree of synchrony between different areas. And even though some synchrony is I believe, necessary for conscious experience, there are some cases that make this difficult to apply in a reliable way in the clinic. Here you can see data from anesthesia, you can see before the medication, and you can see that during the loss of consciousness, the highest state of unconsciousness in this anesthesia session, you have high synchrony, but the subject was completely unaware. And again, you have here an epileptic seizure with hypersynchrony, and the subject was again unaware. A different proposed measure was entropy, under the assumption, again, that consciousness requires some complexity or some different orchestration of functions and so on that would create higher entropy than in unconsciousness. And here you can see two recordings, this one resembling the awake state of this subject, and this one resembling the unaware state of this subject. But if you look at the conditions, you can see that this was an unconscious subject suffering from an alpha coma, and this was a subject suffering from an epileptic seizure, but that was not associated with a loss of consciousness. He was still conscious, and it was a boy. So almost 20 years ago, Tononi and Edelman proposed the idea that consciousness was associated with complexity in the sense that it requires to arise, it requires a network or a system that that has a balance between differentiation and integration. In this case, integration would correspond to the synchrony that we saw before. I mean, different areas being connected and doing similar things. And differentiation would correspond to entropy in the sense that each area is specializing on something specific. So complexity would be a step in the middle in which you have some differentiation and some integration working together. So at this point, Marcello Massimini decided that instead of using an observational approach, that is, instead of looking at the brain without touching it and seeing what it's doing, he said, why don't we perturb the brain and measure the response? Because in this case, we don't need the input. So the idea is that if you stimulate a node on a fully differentiated network, you would see a response that is mainly local and other areas that are not responding. On a similar vein, if you stimulate a network that is fully integrated, you would see a response that is very, very similar between the different areas. And of course, if you stimulate a network with a complex pattern, I mean, with balances, differentiation, and integration, you would see a response in which you can measure or you can extract a set of causal interaction between the nodes that gives rise to a complex response. So how would this be translated to the clinic? Fundamentally, this does not require input or output because we just perturb and measure the brain. How would this translate to a clinical setting? One technique that could be used that is relatively inexpensive and not easy to use, but maybe easier than others, is to use Tms EEG, in which a magnetic pulse stimulates the brain, that is, it's produced by this coil, and we record with EEG the response of the brain. So if we look at a response of a brain that is sleeping, you can see that mainly the response is just a slow wave, a big slow wave. Instead, if we stimulate during wakefulness, we see a very complex pattern of activity as shown before. And again, if we look at REM, we see a complex pattern of activity because here subjects might be dreaming or having some kind of experience. The similar thing happens with anesthesia. If we stimulate during anesthesia with anesthetics that are associated with loss of consciousness, you see very stereotypical responses. And if you stimulate during ketamine, in which subjects typically report having hallucinations and dream-like states, you see again a very complex response. And this here is important that we can ask afterwards to the subjects if they were there or not. I mean, if they were having some kind of experience, and then we can see how this subjective experience correlates with the brain measurements that we are obtaining. So how can this be formalized in an index, in an objective index that could provide an indicator of the state of the subject? So in 2013, Adenauer Casali, together with Marcello Massimini, they said, okay, we can start with the response to a TMS that we have. I mean, we stimulate a point and we measure the whole brain. Here you can see each one of these traces corresponds to one of these channels. And he says, okay, we can perform source modeling, I mean, source localization of this activity to obtain a set of activations on the cortex. We then apply some statistics to determine which sources are significantly active and create a matrix of activations that each one of these points here is an active source at a single time point. We sort this by the overall activity. We use a Lempel-Zip compression algorithm, the same one that is used in many computer applications. We apply a normalization, which is done by the entropy of this matrix, which provides a scalar value that might be a reliable index of the complexity of the response, and therefore of the complexity of the capacity for consciousness, the capacity for complex responses of the brain. So here you can see on the top panel the two conditions, I mean, all three panels, two conditions: wakefulness and non-REM sleep or anesthesia. Here you can see the source current density, the overall level of activity of the sources, and you can see that this does not distinguish well between the two populations. The same happens with the number of significant sources, but if you look at the PCI value, this perfectly discriminates between these two states. On the panel down here, you can see the signal-to-noise ratio and the entropy of this matrix here. And you can also see that this does not discriminate well. You have subjects that were unconscious that are higher on this level than subjects that were conscious here, and the same on the other axis. So again, this goes beyond the level of activity and beyond the entropy of the response. Then, how can this be applied? How can this be applied on a clinical setting? So basically, the idea is that we can have a benchmark population, we can have a benchmark population that is subjects that can report if they were or they were not there while being stimulated, that is subjects under anesthesia or subjects that were sleeping. We can perform this measurement on all of these subjects and then establish a boundary, a threshold that could be used to be then applied on patients. If we do this, we obtain a value of 0.31, and it's important to note that this is not a magical number. This is not if you have 0.32, you are conscious, and 0.29, you are not. This is just an empirically determined threshold that is useful for the clinic. So if you have 0.5, you are not less conscious than someone that has 0.6, for example. So if you use this to assess patients, you can see that on minimally conscious state patients, there are only 2 patients that are not detected. This here is an almost 98% of accuracy of sensitivity. So compared to the 5% that we've seen before, this is a major breakthrough. If using it with vegetative state patients, you can see interestingly that we have kind of 3 groups. The first one is a group with no response, where the brain is not responding at all. These are typically patients with anoxia or a severe brain injury, where you have no response at all. Then we have a group in the middle, with a low complexity response that resembles the response during sleep. And then, interestingly, we have a group with a high complexity response. And very, very interestingly, some of these patients, there are some stories of these patients afterwards recovering consciousness, or I mean, this could indicate that these patients should be looked in more detail, because they might have a higher capacity for recovering consciousness afterwards, after proper treatment. So which could be some mechanisms that underlie this loss of complexity during unconsciousness? If we look at the sleep response, as I mentioned, you can see that this is mainly a slow wave, and this resembles spontaneous slow waves occurring during sleep. And these slow waves, if you look at the cellular level, you can see that are associated with what is called an off period or a down state. That is a period of neuronal silence, a period where neurons stop firing. So we hypothesize that this could be the mechanism that is behind what we observed in here. But unfortunately, having this level of detail, this resolution in humans is very, very difficult. But fortunately, this down state is associated with decrease in the power of the high frequencies when measuring the local field potentials that Gabriele was talking before, for example. What we could use is the stereo EEG patients, I mean the patients that are candidates for surgery and that have depth electrodes, to measure if this response in sleep is associated with a suppression of the high frequencies. So if we stimulate a point, for example, here, and record a different point, you can see 3 examples here, you can see that during sleep, you have this suppression of the high frequency that resembles what is observed during the down states. Importantly, if you look at the phase locking of the activity with respect to the stimulation, you can see that during wakefulness you have like a phase locking that is still significant, up to more or less 500-600 milliseconds. But during sleep, after the appearance of this suppression, the phase locking factor goes down, showing that even though neurons may recover their firing rate, they are doing it in an unordered manner and not linked to the stimulation point. Okay, but does this resemble what we see when we do the TMS stimulation? What we did is to add the EEG cap on top of the intracranial electrodes. So now we have the temporal and spatial resolution of the intracranial electrodes, but we have the spatial coverage of the scalp EEG. You can see again that on sleep you have the typical slow wave response, while during wakefulness, both intracranially and on the scalp, you can see a more complex response. Is this like the TMS? If we look at the, sorry, my pointer is dead, okay. So if we look at the response, you can see during wakefulness, the typical spreading of the activity that comes and goes, that moves around. And if we stimulate during sleep, you can see that the activity mainly remains local where you stimulate it and then dies. If we look at the traces, we again see on the non-REM stimulation that you have the high frequency suppression. And interestingly, if you record very, very close to the stimulation site, you still see some suppression during wakefulness, and we think this is linked to the intensity of the stimulation. This is a very, very high intensity stimulation, which probably creates a lot of inhibition in the surrounding areas. So some work in progress that we are doing on this regard. Under the framework of the Human Brain Project, we are creating a multi-scale platform of analysis, a multi-scale analysis, in which we combine the TMS that I already shown and the intracranial data that I've already shown. And we also used rodent data. This is done by Alessandro Arena at Oslo, where he shows a very, very similar thing, a complex response during consciousness and not so complex during unconsciousness. We are also doing slices with Mavi Sanchez Vives in Barcelona. And we are combining all this with simulations at the whole 3 levels to complete the full circle. And all this data will be available at the end of this project. We are also doing a similar analysis on the patients, on the epileptic patients, because some of these patients, before going to the surgery, I mean, in which a part of the brain would be removed, there is a technique that can be applied before, that is radiofrequency thermocoagulation, in which there's the current passes between 2 contacts, burning the area a little bit to create a small lesion that might avoid the need to go to major surgery. And what we've shown is that if you look close to the lesion side, and here it's important that we have a before and an after recording. I mean, we have the recording before the lesion and right after the lesion. That's what you can see here in black and gray. You can see that if you are close to the lesion, you see the slow waves appearing. And if you move farther away, they tend to disappear. This is a quantification of the delta activity of these electrodes. And you see that this increase in delta activity is for approximately 3 centimeters. If you look at these slow waves that are produced, they are also associated with a suppression of the high frequency, very similar to the suppression observed on the same contact on the same patient during sleep. And this is very, very similar again to what is shown using TMS in patients. Not only that, but we also shown that if you measure the connectivity between the lesion site and other distant sites, you can see that the more connected these electrodes are, the more likely these distant contacts will show slow wave activity. Another thing that we are doing is we are trying to create a perturbational atlas. This is an atlas of the complexity of the responses while stimulating different parts of the brain. And obviously, due to the small coverage of a single stereo EEG patient, this project requires lots of patients to be able to cover the whole brain. Here you can see data from only a few subjects. I mean, we have collected 67 subjects, but we have only pre-processed 27 for now, because this requires a lot of manual labor. So here you have some 27 subjects and the electrode positions. And what we would like to create is a map of how complex are the responses as a function of where you are stimulating. Here you can see some preliminary results where some areas start to show up, mostly in the parietal cortex. This is the back of the brain. This is the front of this flat map. So some contacts are starting to light up, but still this is very, very preliminary because of the small number of subjects. So that's it. I would like to thank everybody at the University of Milan and the Hospital Niguarda. And if you have any questions, please let me know.
Thank you very much for this very nice talk. Let me check if there are any questions from the audience. In the meantime, I actually have a question. I hope not too silly, but it's more a curiosity. Do you think it may have sense to apply this complexity-based measure on, for example, patients with neurodegenerative disease like Alzheimer or Parkinson for quantify the mild impairment? Maybe in that case, it's not necessary to stimulate with EMS. You can stimulate with more standard task, but any way to try to apply this complexity-based measure in that case.
Mm-hmm. Yeah, I think that I mean the index, the exact value that you get is not meant to address. I mean, it's more like a categorical thing. I mean, it's more to say yes or no, not so much to say how much if it's conscious. So I don't know if it's been tried. It could be interesting to do it. We started to try doing this same thing with peripheral stimulation, so it's feasible. I'm not sure if it has the resolution to provide an index on patients. So, I mean, maybe in advanced stages, something could be more evident, but I'm
okay, I understand
it
it.
Would be interesting. Yeah.
It may be not easy to understand the fuzzy nature of impairment. Okay, I understand, but okay, good.
I don't know if it has the resolution to distinguish that. Could be interesting.
Okay, thank you very much. Let me check again if there are questions. I see a question by Alberto. Please, Alberto, you can unmute yourself. Okay.
Yes. Thank you, Ezequiel. Beautiful, beautiful presentation. I have a curiosity. So in the slide in which you showed that with this complexity index, you could like cluster patients in 3 different groups.
Yeah.
So basically, well, one group is very easy. There is zero response. But the other, like the threshold, was it like data driven or?
Yeah,
or,
in fact,
I mean.
Yeah, the threshold is determined by this benchmark. So here, what has been done is you get sets of subjects that can respond and say after the stimulation, were you having some kind of experience, for example, because they were sleeping and maybe they say, yeah, no, I was slightly sleeping, I had something, and they say, no, I was not there at all, I was sleeping or under anesthesia and so on. So you use this benchmark population that can reply and give you an answer to set up the threshold. The threshold simply corresponds to the highest number observed on the unconscious part of the benchmark population.
Cool. So it's basically behavioral in some sense.
Yeah, it's data driven. I mean, it's empirical.
Self. Yeah.
Yeah.
Okay. Thank you.
You're welcome.
Thank you.
There is a question from Annalisa.
Hi, Ezequiel.
Hi.
Very, very nice talk. I have only a curiosity about the TMS stimulation. Which site do you stimulate? If there is some particular site?
Yeah. Yes, I mean, there is a big problem with TMS EEG stimulation, that TMS might not only stimulate the brain, it may also stimulate muscles that are, for example, temporal, all the muscles that are on the head. And if you stimulate a muscle, you get a huge artifact on the response, and this can create complexity on the response. So it's very, very important to standardize the technique. But up to now, typically you can only stimulate on the midline because you don't have muscles there. So you can stimulate from parietal to motor, premotor, and some stimulate on the frontal, but it's a bit dirty. So I would say only on the midline and close to the center, because if not, you get lots of artifacts and everything gets complicated.
Okay, thanks. Thanks a lot. And another question about the threshold that you show also to Alberto is a value that you have to recalibrate, or? Yeah,
I mean, there are up to now. In fact, we did a survey. There are around 180 studies showing this application of the complexity, not all with PCI and so on, with similar measures. But for now, this has been applied. I mean, in 1, 2, 3 papers with different populations. And yeah, you can. I mean, if you get more patients, you can rerun it and adjust it, but it mainly stays there.
Okay, thanks a lot.
You're welcome.
Very, very interesting.
Thank you again, Ezequiel. Let me check if there are other questions. It seems not, so a virtual clap for this very interesting talk.